This is a related rates example. Before doing this example, you should look at the introduction to related rates. Okay, so here's our first real live related rates example. We're given a problem. Air is being pumped into a balloon, and we're told it's a spherical balloon. All our balloons are going to be spherical because we know the formula for the volume of a sphere, and we don't have a good formula for the volume of a normal elliptical balloon. So we have a spherical balloon, and air is being pumped in at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing? So usually the very first thing that we do is make a diagram. This is a spherical balloon, so we're just going to draw a diagram to remind ourselves what the shape is and what the radius is and how the radius relates to the volume. The volume of a sphere is 4/3 pi r cubed. It's very nice that the volume is a function of one variable, the radius. So in all of these problems, we ask ourselves, what derivative do we have? What were we given? And in this case, it's very clear. We were given dV dt, the rate that the volume increases, and we're told it's 100 cubic centimeters a second. So we write that down. And then what derivative do you have to find? That's always how these problems go. You're given a derivative or two, and you have to find one. We have to find when how fast does the radius increase when the volume is increasing at a rate of 100 cubic centimeters a second. Now the other thing we're given is very important. We're told when we want dr dt. Because after all, dr dt isn't constant. Dr dt is changing. And we want dr dt when the diameter is 50 centimeters. And that's just a little tight, slightly tricky thing. You have to turn that diameter of 50 into a radius. And when the diameter is 50, the radius is 25 centimeters. So that's a moment in time when the radius is this size, and that's when we want dr dt. The next step, let's erase that little piece. The next step is to take the derivative. What are we taking the derivative of? We're taking the derivative of the equation that relates the derivative we have, the dV dt, with the variable whose derivative we want, dr dt. So volume, as we said before, is 4/3 pi r cubed. And we take the derivative of this equation with respect to time. We're using our understanding of implicit differentiation. Functions can be anywhere in the equation. And chain rule. We can have functions of functions. So dV dt is, here's the constant, 4/3 pi. Remember, pi is a constant. And now we have the derivative of r cubed. Remember, r is a function of time. So this is chain rule. First, the derivative of the function r, that's being cubed, so it's 3r squared. And then the derivative of r with respect to time. The derivative of r cubed with respect to r is 3r squared times the derivative of r with respect to time. Okay, then we just simplify this. 4/3 times 3 is 4. And then we plug in what we know, which is that r is 25 centimeters. Once we plug it in, we plug in dV dt is 100 cubic centimeters a second, and r is 25 centimeters, and we're going to square it. Then everything here is a constant, and we could solve for dr dt. So it's just simplifying now. Just make sure you're careful with the units, because that can really help you validate your answer. 25 centimeters squared is 25 times 25 square centimeters. And then we divide both sides by the coefficient of dr dt. 4 pi times 25 times 25 times centimeters squared. We divide both sides by that odd quantity. And notice that, well, the 4 times 25 gives you Let's kind of make that visual. So 4 times 25 and 100 cancel, because 100 divided by 100 is 1, and we're left with 25 pi in the denominator. But the other thing we have to notice is that centimeters cubed divided by centimeters squared just gives us centimeters. And the per second stays because nothing divided it out. So we have what we would expect for dr/dt, a linear measure, centimeters per second, and the answer is 1 over 25 pi centimeters per second. And we've solved our first sort of complicated related rates problem.